Hey guys, welcome back. Recently, we did our Hello World example with threads, and today, let's talk about state and resource sharing as it pertains to threads and concurrency. So as we discussed, the operating system allocates resources to a thread, such as stack memory, CPU, and access to other resources. And then the operating system will schedule each thread on the CPU. So we looked at this a little bit when we were passing state to our thread handler. We learned that we can share heap memory and static memory, but sharing local variables and stack memory with the thread is not such a good idea, because each thread has its own local memory, its own stack memory, whereas the thread will share virtual memory with the entire process. And that's what we're really going to dive into today. So all threads are peers. There is no hierarchy, although I use the terms parent and child to illustrate a point where one thread creates another. From the CPU standpoint, there really is no difference. There's no special treatment of threads. Each thread has its own life cycle, independent of other threads. But there is one exception to this. Now, if the main thread of a process dies, all other threads in that process are terminated. You'll recall that we learned that each process has at least one thread. In the case of a C program, as we saw, that main thread is the main function. And now if the main function were to return or to call exit, all other threads in that process will be terminated and the process itself will be terminated. Multiple threads of one process share that process's address space, like heap memory. So we touched on this a bit. We'll look at a visualization in a moment. But for that process, there are certain resources allocated to it, and those resources are shared by all threads in that process. Now, a resource allocated by one thread is visible to others in that same process. So later, this will get into some ideas called synchronization. We'll talk about how state sharing really works across threads, how threads can communicate. This gets into some really tricky business that we'll dedicate quite a few videos to when we get into the more complex topics. But basically here we're seeing that virtual memory in a process is shared across all threads of that process. Now, what is that memory that the process has? Well, a process is memory for data segments, code segments, and the heap. A stack, however, is used for each independent unit of execution. And as we learned, we defined a thread as an independent unit of execution flow. So this follows that each thread in that process has its very own stack. Now, threads of the process can all access and modify the heap memory. So again, that shared memory from the process, all of the threads can perform read and write operations on that memory. And again, that gets into synchronization and race conditions that we'll talk about later. So this stuff gets kind of hairy. We'll dedicate lots and lots of videos to it, but this is the big difference between how heap and stack memory is going to be treated when you're working with threads. Now, the process uses its virtual address space to allocate thread stacks. When we create a process, we have a certain virtual address space allocated to that process, and the process can use that free memory to allocate stacks when we create new threads within the process. Threads are often deemed lightweight, and this is because they mostly use the pre-allocated resources of the main thread. So those resources that the process has allocated to it, i.e. the main thread, those resources are technically pre-allocated. So when you create a thread off of the main thread in your program, things like memory page tables are already configured, shared libraries are already loaded. If you've opened file descriptors in the main thread, they don't need to be opened again. Threads can just use them. And likewise, when the thread is terminated, there is very little cleanup to do. So what we're really saying here is that you have a process. When you create a process, you allocate certain memory to it. The process does a lot of configuration, or rather the kernel does a lot of configuration for that process. And now that the process is running and you're creating threads inside of it, the only thing the process really needs to do, or the kernel really needs to do, when you create a new thread is allocate stack memory for it and execute it or schedule it. You don't need to allocate any heap memory. If you've opened any file descriptors, such as a socket in the main thread, you don't need to reopen those. Really, you're just creating a stack, You're running this thread, and then when the thread dies, when the thread is terminated, the only thing you're going to do is clean up the stack. All of the other memory in the process is still going to be there until the main thread exits and the process dies. So the takeaway here is that threads share virtual memory of the process, but not the stack memory. So again, we have that process-wide memory that all threads can access, and then each thread itself will have its own stack that cannot be shared across the threads. And so on the right here, we have a visualization. We have an illustration of the memory layout of a process P1. And we'll start from the bottom here. This bottom section delimited by the dotted line called shared virtual memory. So this is all the memory that is technically shared across all threads of the process. At the very bottom here, we have the code segment, followed by the initialized data and the uninitialized data segments, followed by the heap. And then in this top section here, we have the P1 stack. This is the stack that is allocated to the main thread of the process, so we've labeled it P1. And then here we have the T1 and T2 stacks, which are the individual and discrete stacks allocated to the T1 and T2 threads, respectively. So in this process, we have 3 threads. We have the P1 thread, or the main thread, and then we also have 2 other threads that presumably were created at some point in the main function's execution flow, the T1 thread and the T2 thread. So inside this process P1, we've allocated 3 separate stacks, and these are not shared memory. And when each of these threads is created, the only thing we need to allocate is the stack memory. We don't need to allocate the heap or any of these things in the shared virtual memory segments. And then when the thread is terminated, the only thing we need to deallocate or clean up is that stack in that context, with the slight exception of the P1 thread, which is the main thread. If that's exiting, then we're also terminating the entire process. So that's it for this one. This is state and resources with threads, at least a soft introduction. Make sure you like, comment, and subscribe. We have a lot more videos coming in this series. We're going to get into a lot more complex topics, so definitely stick around. Thanks for watching. Bye.